So to carry on the conversation, and again, I know we're starting early, but hopefully we're capturing everybody. This will be taped as well, so it'll be available later as a recording. We have Dr. Joanna Tisinski, and she is from NIWC Pacific, my old stomping grounds up there, and she is going to be talking about quantum information processing technology. Thanks for joining us, Joanna. Please, please say a couple words about yourself.
Oh, yes, thank you. Hi, everyone. So I'm Joanna Ptashinsky. I'm at the Naval Information Warfare Center Pacific, which is here in San Diego, California, on the point of beautiful Point Loma. And I have several roles at the center. So in my first role, I am the branch head of the Cryogenic Electronics and Quantum Research Branch. In my second role, I am the center's quantum shepherd. So what I've been trying to do is to bring up and mature all of the main four quantum areas: computing, communication, sensing, and materials. And in my last role, I am NAVWAR's liaison to IARPA. So if you're not familiar with IARPA, it is kind of like DARPA, except that it serves the intelligence community. So today, I'll give you a little bit of a background and information about what we're currently doing with quantum information processing technology at NIWC PAC. And actually, also a little bit broader across the Navy, since we are collaborating with a lot of the other warfare centers and NRL. So why do we care to use quantum information technology at all? Well, it becomes important when it comes to communications, especially secure communications and cryptography. It is extremely important with sensing, so it can be used for covert detection, imaging, as well as detection of corrosion. It's also another important area of computing. So quantum computing can be used for running operations research type of problems. So those would be logistics types of problems that we care about within the Navy, as well as machine learning, AI, and doing risk analysis. And especially with the risk analysis, there are people out in the private sector. So these are more of the financial Wall Street type of people that are very much interested in risk analysis and have been utilizing present day, albeit a little bit immature quantum hardware in order to run those problems to help inform their portfolios. So with communications, how does quantum information technology help for comms to be more secure? So I think a lot of you are probably familiar with quantum key distribution. So for quantum key distribution, we are able to send out secure quantum keys, and let's say those are based on photons with either vertical or horizontal polarization. So whatever that happens to one of your entangled photons, that will be automatically reflected within the second photon. But for traditional quantum key distribution, it is, I guess, still not ideal to use because there are a lot of non-quantum components that are involved. And then additionally, the rate is not really, or your security rate is not really always 100% if you do have an eavesdropper. But people have been moving more and more towards doing quantum networking. So that's where we're trying to build up an entire network of quantum components. For quantum sensing with covert detection, what you can use are, for example, these things that are called superconducting quantum interference devices, or SQUIDs. So squids, yes, a lot of them are at 4 degrees Kelvin, so those would be low temperature superconductors, or at around 70 degrees Kelvin, which is high temperature superconductors. So it turns out that these squid devices are in fact excellent RF sensors. So this is what we have been doing at NIWC Pacific. We have an entire group called the Cryogenic Exploitation of Radio Frequency, which is utilizing those squid sensors in order to, for SIGINT application, just to see what's out there.
What code do you fall under at NIWC PAC?
71730.
So S&T, Science and Technology?
Yes, that is correct. um, so anyway, so that is the SURF group. And what really separates them apart, so let's say if we're to use low temperature superconductors at 4 degrees Kelvin, that means that the cryocooler will be as big as the size of this podium. So that's kind of large to put it onto, let's say, an unmanned aerial vehicle. But with high temperature superconductors, what those allow you to do is to really minimize the cryocooler. So that way the cryocooler will be the size of my water bottle. But unfortunately, high temperature superconductors are notoriously difficult to work with. Just to fabricate the chips, oh my goodness, is that a process? And in fact, there is no entity within the entire United States of America that has the high temperature superconductor fab. So what we did.
Where is that fab?
There are none, so we decided to stand up our own.
Great.
Yeah.
Leading edge.
Yes, yes. So there are a few universities that are working with HTS, but then what you're going to get out of those are like these onesies and twosies. And, you know, it's not going to be a repeatable process necessarily. So what we really wanted to do is, you know, just have our own and have our own capability. So that is what you can do with the superconductors. Another thing that you can do with quantum sensors is to use them for imaging. So let's say if I'm trying to image bacteria, and these bacteria are really difficult to see with a traditional microscope because the resolution is just not good enough. So what I can use are entangled photons. So the number of entangled photons will increase your resolution by precisely that amount. So n number of photons equals resolution increased by number n. So then you are able to be able to image these bacteria. So then you're probably thinking to yourself, well, okay, cool, who cares? And why not just use a shorter wavelength? But if we're to use a shorter wavelength, then we can fry those bacteria. So this is where quantum imaging, you know, becomes important as well. And why do we care about bacteria? So within our waters, we have a certain ecosystem. And sometimes you can imagine, for example, our adversaries interrupting that ecosystem, which will then directly affect everything around it. So this is the reason why, you know, we also care about the marine life and the marine environment. And actually, we do have a couple of environmental sciences branches within NIWC Pacific to look after precisely that.
What's the resolution compared to, say, a traditional transmission electron microscope? And can you use that for microorganisms or a TEM?
So
Just curious.
Yeah, I'm not sure that you can use a TEM. I know
I was
that
wondering
you
about that.
definitely cannot use the SCM. So with the SCM, what you would need to do, so for any sample that is not coated with metal or not metallic, what you're going to get is charging. So with the SCM, you're throwing all of these electrons at your samples as compared to photons. So then you get this charge buildup, so it looks like just this big bright spot. So normally what is done, so let's say if you have a dielectric sample, which is, I don't know, silicon dioxide. So then what you would do is coat it with a very, very thin layer of less than 10 nanometers of, let's say, gold or silver or some metal. So then you're able to see that under the microscope. Also, with a traditional SCM, the vacuum. So the bacteria or live organisms would
Wouldn't
not be
survive
able-
anyway.
No, won't
Yeah.
survive it.
Okay.
And another area where we can use quantum sensing with respect to corrosion, or at least another item that we can use are those squids. So it turns out that the superconductors are very, very sensitive to magnetic fields. And certain metals, when they undergo the corrosion process, emit a magnetic field. So then you are able to sense the changes in the said magnetic field even under multiple layers of paint. So I thought that is really cool, especially since many of our Navy ships do have issues with corrosion, since seawater is the most unforgiving environment. So for quantum computing, the area that I generally care a lot about because it falls within C4ISR is operations research. So let's say if we're trying to position our resources in a particular manner. So let's say we're in a conflict with some adversary, and now we want to know how to position all of our assets in order to gain the best advantage. And now let's say that that adversary winds up taking out one of our ships. So now how do we reposition everything, all of those assets, in order to still maintain that advantage? Let me jump to the next slide. So at NIWC Pacific, we have been doing quantum information technology for a very, very long time. It all started back in the early 2000s. So that's when we did our very, very first quantum entanglement experiment. And that experiment was done by Dr. Mark Roberts and Mark Lasher. So at the time, quantum entanglement was new because we had just been able to develop the materials, the nonlinear materials that allow for entanglement of two photons. So their very first experiment was exploring using quantum entanglement for communications. A little bit later, or actually a lot later, so fast forward to 2016. At that time, the world's very first, and I'll do this in quotes, quantum computer came online, and that was the D-Wave. So the D-Wave is a quantum annealing system, which is a bit different from, let's say, the gate-based IBM quantum processor. So at the time, that was the only hardware that was publicly available. So we decided that, cool, let's try it out. So what we did was we put together a Navy or NIWC Pacific Innovation Jam where we took people's problems that they brought to us, which they thought would be cool to run on the system. And then the winner of the Innovation Jam received access to the D-Waves processor. So at the time, since D-Wave was still relatively immature, it was a little bit challenging to, for example, map your problem onto their system. So first you had to go through this Excel spreadsheet and so I guess the company, it's difficult to invest in everything all at once. So they were investing in their hardware and then the user interface was just a little bit behind. So a little bit later, so this is circa probably 2020 or so, somebody in our Hawaii group was working on the quantum dot photo emitter. So the idea behind this project was to emit single photons. And a little bit more recently, we have actually, this was 2 projects, quantum illumination. So generally, if you're, so for quantum illumination, I guess the closest thing in traditional life that I can think that would be similar to it would be, let's say, quantum radar. But to do something like quantum radar with entangled photons is very, very difficult. So it's a lot easier to do that in the optical regime because with optics we had about over 20 years of experience, and then nothing needs to be cryogenically cooled, and the materials are readily available, so you can buy your nonlinear crystal for about $1,000 or $2,000. And never mind that the majority of them are actually made in China. But if we're trying to perform the same experiment with microwave photons, then that is considerably more difficult because now we have to work, so now we have to work at cryogenic temperatures, and I don't mean the 4 degrees Kelvin that I mentioned before. We have to work in a dilution fridge. So we're working at 10 degrees millikelvin, which is very, very close to absolute zero. And the materials are, finicky, and there's a special process to fabricate the samples. So we've been getting them fabricated at MIT Lincoln Labs. And then, so doing the entanglement experiment in a dill fridge is definitely a different beast. But let's say, and once we see our entanglement inside of the dill fridge, the next question is, well, how do we get it out to room temperature? And that is another difficult problem in terms of the interconnects. But all of this is definitely worthy studying, just because overall in the last several years, there have been great advances made in the quantum fields overall. So NIWC Pacific has definitely been at the forefront of the quantum revolution. So as I mentioned before, quantum is the future of computing and communication sciences. We have been exploiting new paradigms and novel quantum algorithms and architectures, and I'll jump into that a little bit later in the slides. And what we formed is an integrated community of interest. So you really don't want just for the people with the quantum background to be part of your community of interest. You need everybody. So you need all of the folks with a computer science background, with traditional engineering background, mechanical engineers. And the reason behind it is that eventually these folks are going to be testing the quantum hardware, and they're going to be fielding it and integrating it, as well as making future acquisition decisions. So for quantum computing, one thing that we did is we got together with NRL and with AFRL And at the time, AFRL had, or actually purchased access to IBM's Quantum Hub. So that was the IBM's most advanced quantum computing platform. So what we wanted was access to that platform for, not just for NIWC Pacific, but for all of the warfare centers and NRL. So we did initiate a Navy-wide agreement, and with that agreement, access to IBM's processors is absolutely zero cost to us. So we're extremely grateful and fortunate. So as part of that, we stood up the Naval Quantum Computing Program Office, which right now is a little bit of a misnomer since we don't have any dollars yet. So it's not a real program, or not the type of a program office that you would think of in the traditional sense. The idea behind it is to, at this time, manage access for all of the warfare centers and NRL to that resource, and then to bring in additional resources down the line. So for example, we know that there are other platforms that are coming online, so like IonQ and other companies, so should we eventually bring those under our Naval Quantum Computing Program Office umbrella. We're also in the process of obtaining funding to be able to do more of those problems that are of interest to scientists and engineers across the warfare centers. Presently, on that AFRL IBM Quantum Hub, we have 13 active projects. And I should mention that under each quantum computing project, there are so there's one PI, but then there might be multiple other participants. So 13 projects doesn't mean 13 people, it means more people. And that is presently across 6 warfare centers. Five of those projects are from NIWC Pacific, and I have 3 pending access requests. Actually 4, because I got one more this morning. We have a wide range of topics and applications that are being explored, so quantum machine learning, RF data analysis, weapons reliability, as well as object classification. Another thing that we did was we stood up the very first Naval Quantum Information Science and Technology Working Group. So that is co-led by Dr. Borsuk at NRL as well as myself. The idea is to bring everybody within the Navy, and right now it's Gov only, but to bring everybody within the Navy who has an interest or an active project in quantum information science, bring us all together. So what we've been doing is hosting quarterly meetings where we pass down information that floats to us from OUSD, for example, and we also have guest speakers and use that forum for information transfer and communications, as well as for collaboration among all of the parties who are participating. NIWC Pacific is also a member of the Quantum Network in the Washington, D.C. area. So, to help clarify that, we don't have so that quantum network is called DCQNet. So there are 6 main federal agencies that compose the network. That's NRL, ARL, NIST, LTS, U.S. Naval Observatory, and NASA. Since NIWC Pacific nor AFRL have a direct node on the dark fiber that runs in the DC area, we're associate members. So that means that while we can't help them stand up the network at the moment, because it's just not practical, we're not physically located there, but we do plan to use the resource once it is available. And we have been participating in the numerous working groups that DCQNet has. Another thing that we've been doing at NIWC Pacific is building up our workforce. So essentially, how early we, across the Navy and the DoD, adapt quantum technology pretty much depends on our workforce. So we have folks that are doing the very basic research and development, but we will need people who will be able to perform the production, integration, and deployment, as well as within the entire life cycle, eventually support and upgrade for the systems. Since it can be challenging to find or to hire people who strictly have a degree in physics and quantum information sciences, what I've been doing is hosting training series for our scientists and engineers. And generally, of course, there are many warfighting application areas, so we have a lot of folks who are interested. Okay, so let me go back. So to give you an example of our training series, or at least, yes, so normally I hold the training series every 2 years. So about 2 years ago, the first course in the training is the fundamentals of quantum mechanics. I typically choose a university professor to teach that class since they're well adept at teaching. Yes, for the last one, I had Professor Frank Narducci from the Naval Postgraduate School. So after students go through the 6-week course in the fundamentals of quantum mechanics, my next offering is IBM's Quantum Summer School. So IBM has their summer school every summer. It's a 2-week, very, very intensive course. So it is approximately 8 hours per day. It is free of cost. And during those 8 hours, instruction is for about 4 or 5 hours, and the rest of the time you're expected to write your own programs and work on your assignments. So typically, we have about 10 people or so each year from NIWC Pacific and across the warfare centers who wind up taking that class. We usually will have 2 or 3 who will pass the course with the perfect score, which is something. Because it is taught at the graduate school level, so they have to be extremely focused in order to get the perfect score. And then last in the training series is the Quantum Optics Laboratory. So that is taught out of one of my labs at NIWC Pacific, and it is pretty much hands-on experimentation. So since my background is in optics and photonics, I find it really easy to explain quantum phenomena with optical instruments. So that way we can explore the particle wave duality of a photon. Generally the lab is for about 2 weeks, and we meet 2 to 3 times per week for 3 to 4 hours. So that way students can get a chance to do some hands-on experiments. So we have also been investing in our infrastructure and facilities. We will have a brand new quantum building, and the completion date, oh, I didn't update this, moved. So the completion date was supposed to be in January, so this year, but there was an issue with the subcontractor, so the deadlines kind of slipped a little bit, so now it will be built in June of this year. So the facility, it will not have any offices inside of it, it's just going to be labs. And in order to run quantum experiments, which are very, very sensitive, you need certain environmental conditions. So that was my vision for the laboratory. So you have to have certain humidity levels. example, your ceilings cannot have little particulates falling off of them because that can completely ruin your experiment. We need very, very stable flooring that is able to handle multitudes of optical tables. So if you're not familiar with optical tables, each one of those weighs about 2,000 pounds. So if you have, yeah. So we need the appropriate flooring, of course, anti-static, appropriate power. So we definitely need three-phase power, like for our dilution fridge. So the building will have all of those requirements, and that way we'll be able to conduct a whole slew of experiments as well as consolidate all of our separate little laboratories into one building. There is another building that was completed in 2022, and that is for our surf groups. So those are the guys that are working with the superconductors, with the squids. So for my little quantum optics lab, that was fully remodeled back in 2020, and we'll be moving out of it onto a much better space. And for dilution fridge, we procured that back in 2019. And the picture here, that's actually the inside of the dill fridge. We have been building partnerships, especially through CRADAs. So one partnership that we're in the process of putting together and finalizing is one with SUNY Poly, and that is in the area of fluxonium qubits. We're also working with the Applied Research Laboratory at UT Austin on quantum computing and communications, L3 Harris for quantum networking, and the University of St. Andrews in the UK for structured illumination. Additionally, we do have a bit of international engagement. So we're in the process of putting together or finishing up the project agreement between the US and Korea. And this particular project will be focused on quantum illumination / quantum radar. So it turns out that the Koreans, as far as their research is concerned, are pretty much at the same stages as we are. So it makes it ideal to have a partnership and to learn from one another as we're building our experiments. Another potential opportunity is to set up a project agreement with Finland. So it turns out that the Finnish have an interest in quantum sensing and communications. So for the key takeaways, at NIWC Pacific, we have a pretty long history with quantum. Quantum is definitely growing. There are many applications across C4ISR and space. From my perspective, it is of utmost importance to continue maturing this very critical technology area. Thank you. I will take your questions.
Thank you, Dr. Tuszynski. Fantastic. Any questions out there? Please.
What about PNT? Are you guys interested in looking at how sensing can help with PNT, specifically magnetic navigation, gravitational navigation?
Yes, we are interested in PNT. I believe that Dr. Carrie Moran's group has been working that piece. I know that, so I haven't gotten the latest from Carrie, but I know that she is involved in the transition of quantum sensors program. So that was the OUSD R&E funded program that now moved over to DIU.
I'll ask the same question I asked earlier. Where do you think we stand with respect, in this case, maybe to where the adversary is with respect to our quantum development and adoption? I know you say NIWC PAC's been at it for a while, but as a general answer, maybe across the service or the services?
Yeah, so as far as, so it depends on which area. So as far as quantum computing is concerned, we are definitely in the lead. And that has to do with our amazing private industry that has stood up these systems in a relatively short amount of time that now are available for all of us to use. So even though the systems, may not have reached their full potential, but at least we have something that we can practice running our problems on and get ready for the future. An area where I also believe that we are a little bit ahead of our adversaries is quantum sensing. So out in literature, at least the academic literature, I'm not really seeing anything extremely novel from our adversaries, but I do know that they are fast catching up. With quantum communications, I know that there was the big article or big press release by our friends in China that said that they built their quantum network or satellite quantum network. So we don't have, or at least at this point, we don't really have our own comparable quantum network um, that is similar to what they have built. But at the same time, if you think of all of the cost that's involved and what you get as the return on investment, I think that we are making the right decision. I believe that for us, it is probably more important to mature some of the quantum networking, like what we have been doing under DCQNet, so to first mature those in the lab, so that way we can have a real, quantum network. So, like, what are some of the issues with the one from China? So I believe that the majority of their experiments were done at night, and that is for a reason. So let's say, if you're sending entangled photons, that means that you have very, very few photons. And now, let's say if you're sending those entangled photons during the daytime, so now your photons are competing with sunlight. So there are, I guess, a lot of nuances to these experiments that were showcased. I guess an area where we could also improve is with respect to materials, and I think a lot of you in this room are aware of that already.
What about the community of interest that you stood up with Dr. Borsak? Is that a working group, and how do people, government folks, probably, I think it's constrained to government only, is it?
Yeah, it is
And
government only at this time. Send me an email.
I was going to say, how do people get invited to that, or
Yes, send me
an
an
email?
email,
Okay,
yes.
I have one here.
So, a quick question that maybe doesn't have a quick answer. What are you doing in space, or is a high priority to do in space, and how can industry help with that?
In space, so what we could, so I know that in space, for example, we need very accurate clocks. So those would be extremely helpful. I know that we have looked at, I guess we are looking at doing entangled comms or information transfer, let's say between satellites. So that's a lot easier as compared to going from satellite down to ground, because so normally, with any type of quantum communications over free space, you are going to be constrained by the same reasons as traditional free space optical comms, with the exception that now you'll have way, way fewer photons.
Go ahead.
When you said you need really good time, how good?
So can I jump in on that? Mr. Bilju over at, maybe Dr. Bilju, over at PMW 170 hosts a regular, every other quarter, a slam time event, and every other quarter it's an APNT event where they talk specifically about this. But GPS and position, assured position and timing, navigation and timing continues to be a challenge, especially in DDoS environments where right now we're still relying upon satellite jumps to get to a shore base, to get to the clock. We want to be able to have that on site in space wherever we're at. And I wanted to follow up also on the space optical question. I think some of our industry partners are installing optical transmitters on all of their satellites so they can intercommunicate in space together and speed that process.
Awesome, awesome.
Same question about computing power. Right now, you said you have access to a computing source there. How do people get access to that, or is that only restricted to NIWC PAC and your partners?
Yeah, it is only restricted to NIWC Pacific and the warfare centers and government only.
Here is. And final one for me is, do you have relationships with academic institutions here in the area, San Diego? Any of the universities?
So university-wise, I'll typically, so yes, we do. So both in my group at NIWC Pacific as well as for me myself. So I still keep in contact with my former PhD advisor at UCSD. But we have relationships with the UCSD physics department as well as with San Diego State. And can't recall the professors' names off the top of my head.
Perfect. Last questions. Back there. Here we go. Please use the, hang on, yeah, use the microphone.
So from your early presentation, you described, talk about you can do a single photon transmitter, right? What's the current status to receive a single photon or receive a single electron right now? Do you working in that area?
So we are not building the single photon detectors, but they do, so commercial ones do exist. So for example, we just, this morning, tested in the lab, so there's a company called ARIA that makes these really great single optical photon detectors.
Because to catch the one single photon, that's the ultimate goal for our communication people. Usually we have to send a lot of photon, right, as a waveform, carry information. Transmit one single photon depends on the twist, left or right.
Yeah. Oops. Sorry. Sorry. So normally what you're going to be doing are looking at correlation measurements. So I guess as you're sending out your entangled photons, and it's a small number of them, but nevertheless at the detector, what you're looking at is what's hitting your detector might be like 100,000 photons. So then what you're looking for is a correlation between, say, your signal and your idler photon. So like their arrival times. And then you plot those out to determine, what you actually had.
We all know prove it is faster than the speed of light. So that, based on the Einstein theory, that cannot be carried information, right?
No, yeah, you cannot carry information that way, so.
So the quantum communication means we can send a single quantum bit with information unknown before I send it.
Right, yes.
Can I ask one more question? So in regards to the access you guys have with IBM and some of the research you guys are doing on the NISC processors that are available, can you comment on the nature of problems you're looking at? Are these typically logistics optimization problems, or are they, what are you using QML for example?
Yeah, so I'll comment on a few of them. So, for example, I know that NRL is interested in quantum chemistry. And so, it's like, well, why? But quantum chemistry can be used to develop novel paints that can, for example, help with the corrosion aspect. And they also have a lot of scientists that are, already working in that area. At NIWC Pacific, we are C4ISR, so corrosion, that's more of a NAPC type of a problem. So this is the reason why we're looking at like logistics, but a problem that we ran relatively recently, and I believe there's a conference paper out there. So that had to do with network traffic prioritization. So using machine learning to help us, classify, and quantum machine learning, not regular machine learning, to help us figure out what the traffic is and to help best prioritize it.
That's a great application. In fact, SoftBank did the same thing in Japan using our software. They used QML for, yeah.
Mm-hmm. Yeah. And then another, yes, we are exploring potential problem with like a drone swarm. So we've been talking to various people across the center to figure out, well, how can that resemble a realistic, a realistic scenario that we can still map on the present day hardware. At Carter Rock, what they're looking at is finite element methods. So they're looking at using quantum computers to solve differential equations because they have an interest in the finite element method. And similarly, going back to those differential equations, NRL has a outfit out in Monterey. So those folks are doing a lot of weather prediction, and there's a scientist there that is looking at weather prediction using trying to solve, or using quantum computers to solve those differential equations.
Thank you. That was helpful.
Okay, we got here, please.
Hey,
Hi.
my name's Al Lucchini. I'm an IT strategic planner with NABAIR. You mentioned one of the issues was a need to improve materials.
Yeah.
Can you expand upon that?
So I know that, or with the quantum computing aspect, I guess. So for that, I know that a big issue is corrosion. And aside from this very high level nugget of knowledge that I have, I don't know precisely what the details are or how those quantum chemistry simulations can in fact inform novel paints or novel materials that we can put together that then could be put to good use.
Excellent presentation. Thank you so much. Any other questions, last minute questions? Okay. Thank you,
Thank
Dr.
you.
Kaczynski. Thank you so much. Thank you very much. All right, our next presentation, Dr. Kelly Bax. Are we here? Oh, she is here. Let's see, should we take a 5 or 10 minute break? Maybe a 5 or 10 minute, yeah. And then we'll come back. We'll hear from Dr. Kelly Bax, and we're going to talk about quantum sensors for complementary P&T. Who asked that? There he is. He asked that question. And resilient communications. So let's call it, I don't have my watch is probably inaccurate. 5 to 7 minutes.
Yeah. I still don't know about the last one, though.
Is Dr. Teleska here? AFRL? Dr. Teleska?
Got it.
Jeff, we finished early.